Inequalities can also be solved using graphical methods. Consider this linear inequality. 9 subtract 2x is less than x plus 3. If we could draw a graph of y is 9 subtract 2x and also of y is x plus 3, then if we want 9 subtract 2x to be less than x plus 3, we would need the y-coordinate of this first straight line to be less than the y-coordinate of this second straight line. Drawing those two straight lines then, we need the y-coordinate of the purple line to be less than the y-coordinate of the green line. Let's just pick a particular x-coordinate and look at how those y-coordinates compare. This red line compares those y-coordinates for an x-coordinate of -3. We can see that the y-coordinate of the purple line is much larger than the y-coordinate of the green line. We want it to be smaller, therefore we would not be interested in this x-coordinate. Let's see what happens as the value of x increases. We're still in a region we're not interested in, until we pass through the point of intersection. After that point, the y-coordinate of the purple line is lower down than the y-coordinate of the green line, so these are values that we would be interested in. What we are therefore going to have to do is find the coordinates of the point of intersection, and the graph we have sketched here shows us that every x-coordinate to the right of that point of intersection is one that we are interested in. So what is that point of intersection? Where is 9 subtract 2x the same as x plus 3? Well, adding 2x to both sides and subtracting 3 from both sides, we will have that 3x is 6, so x is 2, and using the graph we can therefore see that the solution to the inequality is any x value greater than 2, or in set notation, values of x which are greater than 2. We can use the same graphical method to solve quadratic inequalities. In this case, we could draw the graph of y is 2x subtract 8. We could draw the graph of y is x squared subtract 6x plus 4. And if we want 2x subtract 8 to be greater than or equal to x squared subtract 6x plus 4, then we are interested in points where the y-coordinate of this straight line is higher up or at the same height as the y-coordinate of this parabola. So drawing that straight line and that parabola, we are interested in places where the y-coordinate of the straight line is larger than the y-coordinate of the parabola. Once again, we'll draw in a line segment to indicate the difference between those two y-coordinates for a particular value of x. We're starting with an x value of -2, and we can see that the y-coordinate of the parabola is larger than the y-coordinate of the straight line. We'll also put in the points of intersection between the parabola and the straight line. Now let us see what happens as we increase the x-coordinate. We're still in a region that we are not interested in. The y-coordinate of the parabola is larger than the y-coordinate of the straight line, but the difference in those y-coordinates is decreasing as we approach the first point of intersection. When we are at the point of intersection, the y-coordinates are the same, and after we pass through it, now the y-coordinate of the straight line is larger than that of the parabola, so this is what we are interested in. However, as we make the journey towards the other point of intersection, the difference in those y-coordinates is decreasing again. When we get to the point of intersection, the y-coordinates will be the same. When we emerge from the other side, the y-coordinate of the parabola is larger than that of the straight line, so we're again in a region we are not concerned with. What we will therefore need to do is to identify what those points of intersection are. Well, we only need their x-coordinates, so we need to solve the equation 2x subtract 8 is x squared subtract 6x plus 4. If we subtract 2x from both sides, and add 8 to both sides, we will end up with this quadratic equation, which nicely for us does factorize into x subtract 2, x subtract 6, and therefore the points of intersection are where x is 2 and where x is 6. And the graph we've already looked at shows us that we are interested in intersection points between these x values, or we are allowed to actually take these x values because we have a greater than or equals. We don't have a strict inequality. Therefore, the solution will be x values greater than or equal to 2, or less than or equal to 6, or in set notation, values of x which are greater than or equal to 2, or less than or equal to 6. We can also use graphs to indicate regions which satisfy a selection of inequalities. Let's look at this example. Draw a diagram which shows the shaded region satisfying the inequalities x is less than 4, y is less than or equal to 2, and y is greater than 1 minus x. The way we should start is for each of these inequalities, we should instead start off by drawing the straight line where we replace the inequality by an equality. So let's draw the straight lines. X is 4, y is 2, and y is 1 minus x. Now why is one of these lines solid and two of them dotted? This is connected with the kind of inequality that we are considering. When we've drawn the line x equals 4, this is going to be in relationship to a strict inequality. In other words, when we finally work out which region is represented by x is less than 4, we are not going to include x equals 4 in there, so therefore we draw a dotted line. The same thing applies to y being greater than 1 minus x. However, when we are interested in the region where y is less than or equal to 2, we would allow the values y equals 2, so we draw a solid line. Now for each of these lines, we have to consider which region we are interested in. If x is less than 4, that is going to be the region to the left of the dotted line x equals 4. If y is less than or equal to 2, that is going to be the region including and below the solid line y equals 2. If y is greater than 1 minus x, it's not immediately clear which side of that dotted line we want. So one thing we could do is just to choose a point and see if it satisfies the relationship or not. So why not the origin, 0, 0? Which side does that fall on? The y coordinate is 0. Is that greater than 1 minus 0, the x coordinate? No, it's not. Therefore, we don't want this region. It must be on the other side. If we now show all three regions, we can see the region where all three intersect. And for clarity, let's remove everything apart from that overlap. So the shaded region is the one that we were asked to draw, and it is very important to draw solid lines when they are included in the region and dotted lines when they are not. In this example, we're asked to draw a shaded region bounded by a quadratic inequality and a linear inequality. As before, we should begin by drawing the curves y is 6 subtract x squared, and the line 3y is x plus 6. The parabola is drawn dotted because that quadratic inequality was a strict inequality. The straight line has been drawn solid because the linear inequality involved a greater than or equal to. We now have to identify the regions involved. For the quadratic inequality, we require y to be less than 6 subtract x squared. Again, it's not easy to see straight away what's going to happen, so if we pick a point, again, say 0, 0, the y coordinate is 0. 6 subtract 0 squared is 6. Y is less than 6 subtract x squared, so the origin is within the shaded region, and therefore that shaded region we require is as shown. For the linear inequality, we require 3y to be greater than or equal to x plus 6. Again, which side of that straight line is it? Well, let's try again the origin 0, 0. 3y is 0, x plus 6 is 6, so 3y is not greater than x plus 6. We are not interested in the side of that straight line which includes the origin, therefore we are interested in this region. And now we can see where those two regions overlap. Removing the original regions, the remaining shaded region is the one that we are interested in. Once again, the straight line boundary for that shaded region is solid, the parabolic boundary of that shaded region is dotted.